This is hydraulic valves part B. This is the second video in a series of hydraulic valves. By now, looking at schematics, you should have a good idea of how these valves work. And again, a lot of these valves, they may look the same, but you have to figure out, are they pilot operated, and really what are they doing in the system? A lot of these that we're going to talk about today, we've already looked at. So for instance, a poppet style check valve. Again, it's just a check valve, and it uses a spring to close it so we only get flow in one direction. When we're taking a look at a rotary spool valve, again, when we look at a schematic, it may not tell us, or it's just a closed center system. So we don't know it's a rotary spool valve. We may have to look at the piece of equipment. Doesn't matter whether it's a rotary spool valve or a spool valve. Again, they both have the same schematic and they both do the same thing. So when we take a look again at the spool, the grooves in the spool retain some oil to help seal the spool so we don't get any leakage. We have metering notches on the spool itself so we can feather the control to move the cylinder really slowly. We take a look, we have an accumulator. We know it's a gas charged accumulator. We have a one-way check, positive displacement pump, a relief valve in the system, and a reservoir. Now, one of the things we didn't spend too much time on is in a control valve we may have 4 positions. So when we let go of the controls, with the spring, it goes back to a neutral position where the controls aren't moving. So anytime we have any issues, if we let go of all the controls, it should go back in a neutral position. Everything should stop. So if we pull back, we have a raised position. We push forward, we have a lower position. We push all the way forward, and there's usually what's called a detent that will go into what's called a float position. And this allows the oil to travel from one end of the cylinder to the other end of the cylinder, back and forth, without us moving any of the controls. Some operators will use this for backblading. So let's take a look at some control valves. So here we have a 2-position 3-way. So as we discussed earlier, we have 2 separate blocks, so we know that's a 2-position. 3-way means we have 3 lines coming in and out. So here's 1, here's 2, here's 3. So where would we use something like this? Well, we could use this in a dump box to raise and to lower. Or we could have it so it goes to some component that doesn't return the oil back through the valve. So here, oil can go out to either A or to B. And again, here's a single acting cylinder, but this is a three-way because we have 3 separate boxes. We know it's an open center system. We have a relief valve. When we go in one direction, it's going to raise it. When we go in the other direction, it's going to lower it and dump the oil back to the reservoir. Here's a 3-position 4-way. Again, we have 3 boxes. We have 4 lines, so we know it's a 4-way. In one direction, the motor turns one way. In the other direction, the motor turns the other way. And we also have a case drain. Now again, when we're taking a look at a motor, a case drain drains any oil that's leaking past the system so we don't build any pressure in the motor itself. And we want to make sure that that case drain is always drained back to the cylinder. And here's a good way to test if, for instance, say the motor isn't functioning properly, doesn't have the power we need, we can just pull off the case drain and drain it into a bucket and see how much leakage we're getting past that motor through the case drain. That may be where our issue is. So it's a good, quick, easy way to check. So 3-position 4-way valve is probably one of the most common that we're going to see. Now 4-position, that is the 4th position is the float position. Again, what it does is really it just opens everything up and allows oil to flow freely back and forth to any type of any end of the cylinder we want. and it can also return the oil back to pump or back to tank. So we've discussed open center and closed center systems. So again, open center systems returns the oil. There's no restriction in the line. The pump runs all the time, displays the same amount of fluid. So here we have directional ports. So again, our system goes through, it returns the oil. No oil goes out to here. There's really no pressure because it can't build pressure in the system. But what happens on this motor? Well, the motor can't turn this way because it's locked. It can't turn this way because it's locked. So that means that the motor really has a brake. We may have some internal slippage or some leakage internally that may allow this motor to move a little bit on its own. But theoretically, this will lock the motor and prevent it from turning. So when we supply pressure to one side, it can go through and allow the motor to turn. As the motor turns, it builds pressure in the opposite side, because again, as fluid's coming in to turn the motor, that other fluid that's in there has to be displaced. It will go out. It can't go out this check, but what it'll do is it will go out and it will run this pilot line that will open up this valve and allow that oil to return back to tank. Does the same thing when we go in the opposite direction. Closed center system. When we have a closed center system, we have to use a variable displacement, or we should be using a variable displacement pump. So we can vary the swash plate angle, and when we vary the swash plate angle, we vary the displacement that the pump's putting out. So the pistons are still turning inside the pump, but because we have zero swash plate angle, we're not displacing any fluid. As the pressure drops in the system, it will start to stroke out and start to displace more fluid. Now, we talked earlier about having mechanical controls on components, and the big issue with this is the control valves have to be close to where the linkage is, so that we can have that linkage without having a lot of components moving, because as these components move, they create wear, and then we're having to always fix that. So one of the things that we've done is we've gone what's called a pilot operated system. So number 4, we have our variable displacement pump, but number 1 is a pilot pump. Now this pilot pump can be bolted to the back of the main pump, but what the pilot pressure is let's just say that the pilot pressure is 300 psi. This is a positive displacement pump. Once that pressure gets to 300 psi, this is going to open number 2 and dump any excess pressure out. Now this pilot pressure here can act on the main control valve and move the main spool valve back and forth to direct oil to the cylinder. Pilot operated systems are great because now we can use low pressure lines and have these control valves inside the cab, and these lines just run out to the valve body that's close by the rotate manifold, and we can control all of these with low pressure oil. So another thing, again, when we're taking a look at a pilot operated system, they vary, again, understanding what the schematic is telling you. So looking at this is a control valve in the cab, so when we move it one way or the other way, it's going to direct oil down to this spool valve and move it one way or another way. We see springs on each end that when we let go of the controls, this will center itself and the spool will center itself and the movement of the cylinder will stop. So another one we might see is an electrical directional control valve. Now these are either on or off when we're dealing with this one. We'll talk about pulse width later. So when we energize one side, it energizes a coil that creates electromagnet that pulls the spool in and allow it to move in one direction. We put it in neutral, de-energizes, and it will go back into the center position. We push it the other way, and it energizes this coil, and we'll pull the spool back into from the right to the left. So, electric over pilot direction control, again, these are on and off, and so we're just energizing one or the other in a pilot operated system. Now, there's another thing that we have is mechanical detents, and you'll see from looking at the schematic, we can have detents on both ends or one end. And all it is we can have a detent and it will stay in that position till we move it out. For instance, if we put it in a float position, so that's on a four-way valve, the fourth position is a float position, we can let go of the controls and it will stay in the float position till we physically move it out of the detent. We can also have an electromagnet detent. For instance, on a boom, I can pull this. Let's say I want to raise the boom as I'm moving. I can have an electromagnetic detent in there, so once it gets to the top of the stroke of the cylinder, it will then kick it out. And how it works on one of these is we have what's called a proximity switch, and the proximity switch controls the ground side of a relay. So when the ignition switch is closed, power comes into the relay and also goes through the coil and goes to the proximity switch. Now the proximity switch, again, depending on how it's set up. So let's just say that it's a normally open switch, or normally closed switch. As soon as I pull it in, it energizes this coil, which is going to pull this clapper valve in. Now it's going to stay in that position until the proximity switch opens the circuit, drops the relay out, and then this will go back into the center position. Now what will cause the proximity switch to drop out? Well, usually what we have is, if we take a look at a proximity switch, we're going to have, as it starts to extend, something's going to come in front of the proximity switch, is going to break contact and tell the proximity switch to drop out. So again, it can be a normally closed switch, and once a piece of metal comes in front of this proximity switch, it's going to drop out, the electromagnet will drop out, and the boom will stop raising. System relief, again, we've talked about system relief and circuit relief. So a system relief relieves the whole system, where a circuit relief is going to relieve the circuit. So we can have a circuit relief on each side of the circuit. If it doesn't have a circuit relief valve, it uses system to relieve that pressure. Load checks. Now, load checks are in the system to prevent the load from dropping unexpectedly until system pressure comes up. So, directional control valve with a load check. Next one's an anti-cavitation valve. So, again, remembering what cavitation is. So, if I want to drop a cylinder, or let's say a blade, really fast, so I would be putting oil to this end. Now pressure, what happens then is oil can't fill this end of the cylinder fast enough. So what it's going to do is take oil from the return side and allow oil to come in to fill that void. So this is what it looks like on a cylinder. So here we have pressure coming in to fill this, to extend the cylinder, and this returns to tank. But what happens when I want to extend that cylinder really fast? The pump can't provide enough oil, so it takes that return oil and runs it into this end of the cylinder to prevent cavitation. Now remember, cavitation is a negative pressure that forms a vapor bubble, and we don't want this inside the system. So this is what this anti-cavitation valve prevents. It just takes return oil and routes it back through the system as makeup oil. It can also be used as a circuit relief. Okay, directional control valves. We may see double check valves in the system. Again, understanding what they do in the system. Now, when we're dealing with valve bodies, unibody is cast all in one piece. If we have a failure of one component in here, the whole valve body has to be replaced. So that's where we see a stack of control valves. And what we'll have is we'll have a piece of bar that goes through here, 1, 2, or 3 bars, that an O-ring seals each individual one. So if we have a valve failure, we just have to remove that one valve body and replace it with another one. Oh, and again, you can see that this doesn't have a relief valve, this one doesn't, and so on. So again, these are going to use the system relief. This one here has a circuit, this one here, and this one here. So again, on the other side, we may or may not have circuit reliefs. So series passageways. So a series circuit, flow has to go through one before it can go through the other. When we get into different types of circuits where we can have tandem, where it goes through this one, then through this one, and returns back to tank. We also have series parallel connections where this goes through this way and returns back to tank, but also has a parallel circuit that can feed another control valve. So open center systems. Now a diverter valve. So what it's going to do is divert the flow. So in our diverter valve, if it's set in this position, this main control valve is used. When we move our diverter valve to the other position, now we can use our auxiliary control valve. So one of the things to look at is what's called a power beyond sleeve or a power beyond fitting. For instance, let's just say I've got a machine that's got a detachable hoe on the back. So I can use a power beyond fitting so that the oil doesn't return to tank through the control valve. It's got to go through the hoses that are quick coupled together for my backhoe. So for instance, if I want to hook up the hoe, I'm going to shut off the machine, disconnect the hydraulic lines, hook them up to the backhoe, start my machine, and then with my power beyond fitting, now hydraulic oil runs to the control valve on the backhoe. And I can use the backhoe whatever I want. When I want to disconnect the backhoe, I have to disconnect the hydraulic lines to the hoe and then couple them together with a quick coupler. And now I could just run the machine. So again, taking a look at different types of parallel connections. And that's the second video of valves.